All right, so we're back. And so I want to talk a little bit about how the template theory accounts for how we can recognize patterns so quickly, even if supposedly we're checking all of the templates, right? One of the things that they argue is that we use pre-processing to simplify the stimuli. So we don't have to look at every single detail of the stimulus in order to start the process of comparing it to our templates. We can just look for glossing, right? Like the fact that it's made of glass or that it could conduct a drink to our mouth, something like that. We let context provide a lot of the clues so that we can dive into a particular part of our memory store that has the memories that are most relevant to this. A good example of these ideas comes from this. Okay, so you can see that this says A, B, C, D, E, F, and then it says 10, 11, 12, 13, 14. You probably even are noticing that the B and the 13 are exactly the same form. The fact that you see that form as a B on the top row and that same form as a 13 in the bottom row indicates that your brain uses context to help you to figure out what exactly is coming in through the sense organs. So the object may be exactly the same, but if it's being seen in this context or that, you're going to make a different judgment. What surrounds it really makes a big impact on what you're perceiving, how you're going to actually draw your conclusions. Another example of that is handwriting. So you probably can read that this says my phone number is area code 604-876-1569, please call. So handwriting is an interesting case because we don't all write perfectly. And so we may make different forms in our writing. In this case, the H in phone and the B in number are in fact the exact same shape, the exact same form, but given the context, we see the one as an H and the other one as a B. The word is the exact same form as the 1-5 in the phone number, and you can tell that it's supposed to be is in one case and it's supposed to be a 15 in the other case, right? These are things that we do when we're trying to interpret information, is that we use what we are able to understand. We see that there's a phone number coming up, so when we see the words phone number, we're predisposed to see those as phone and number. We already are in a certain part of our template is the basic idea. So these examples help us to understand how maybe template theory might work. Another example is not quite as verbal. Here we have the moon illusion. And if you've ever seen a full moon on the horizon, maybe rising up behind some trees or behind some buildings, it oftentimes looks really big compared to what the full moon looks like when it's in the middle of the sky with nothing around it. Like on a clear night, there are no clouds obscuring or anything. It's just the moon in the middle of the sky. In fact, some people think that the moon is literally closer to us when it's on the horizon. Some people actually believe that. It's not true. It's negligibly true if it is true at all. The reason why the moon looks bigger on the horizon is because of context cues. You know how far away that house and those trees are away from you. And you might even be misestimating it too. You might underestimate or overestimate how far away that house is. And so that might play a role in how close you think the moon is. But when you have things that are on Earth and of a reasonably knowable size, and then you have the moon behind it, and you mistakenly believe that the moon is farther away than it is. A lot of us overestimate the distance of the moon when we're asked how far away the moon is from us. So if you put those two things together, context cues and then not really knowing how far away the moon is, it looks really big when we say, wow, the moon is so far away and it looks so big relative to these things that I know are close to me. And so it causes us to overestimate the size of the moon. We also think that the moon is taking a closer path to us when it's higher in the sky. We think the moon's closer to us than it really is. So when we look at it in the middle of the sky, we think, wow, it's so close to us, and yet it looks so small in that empty sky. And so that perception, that drawing of conclusions about the sensation coming into our eyes makes us make these incorrect assessments of the size of the moon in the different positions. If you want to test what I'm claiming, you can take a nickel, which turns out to be exactly the diameter of the moon when held fully extended in your arm. So hold a nickel fully extended It'll just cover up the moon. You'll see just a little brightness around the full moon as you're holding the nickel around it. And then do that at the horizon, do it up in the middle of the sky, and you will see that the moon is exactly the same size. It fits exactly behind the nickel in the exact same way, whether it's on the horizon or it's in the center of the sky. So any appearance of it being bigger on the horizon has to be perception, not sensation. It has to be your brain taking context into consideration and drawing some incorrect conclusions about distance and other kinds of things that makes it seem like the moon's a lot bigger than it really is. So that's a little home experiment you can do. Next time it's a full moon without, clouds obscuring it, go out there with your nickel and go check it out. It's the same size in all positions, and all you're left with is we're drawing the wrong conclusions. We're relying on context when we probably shouldn't be, in this case, to make our perceptions. Another good example of how context helps us to understand what we're perceiving and, allowing us to compare to templates and so on is the Wundt-Gastro illusion. So Wundt is Wilhelm Wundt. So this is a really old illusion that has been around for 150 years at this point. What we have is two arcs. We've got the red one and the blue one here. And I'm going to tell you they are the same size arc. I created these on the screen myself, and I just copied the same shape, and I colored one red and I colored one blue. But the one on top should look bigger to you right now. And what Wundt and Gastro argued is that the reason why the one on top looks bigger is because you're comparing the long curve of the red one to the short curve of the blue one. And that's causing your brain to make the conclusion. Your sensation is accurate. Your eyes are collecting information that's showing that those two arcs are the same size. But when your brain is interpreting what's coming in, it's saying, that long arc on the red one is so much bigger than the short arc on the blue one. The red one altogether is bigger than the blue one altogether. Now I'm going to show you a little animation here. Now the red's on the bottom. You saw it pass through and it was the same size, right? So watch it pass through. Now it's on the bottom and the red looks smaller. So that happens because of this context effect that our brain is taking into consideration. In its experience, comparing it to other templates of things that you have experienced out in the world, when something on top looks longer like that than something directly beneath it, it's because the thing on top is in fact bigger. Like that's, your brain is playing the odds. And in the past, when it's looked bigger on top, it's because it's bigger. And so you maybe have this illusion in part because your brain is drawing this incorrect conclusion based on its previous experiences. Now the great thing about illusions is that we have to go through some pretty clever design to get it to happen, to have you have this incorrect interpretation. There aren't as many things like the moon illusion where out in the real world we all have this experience where we're seeing something wrong. That doesn't happen that often because generally our brains do a really good job of figuring things out. We have to go through a lot of different machinations to get an illusion to emerge where we all are seeing the same wrong thing. So let's jump into another explanation for how you recognize patterns. This one's called analysis by synthesis. And one of the things I'm going to start off with is how faces are really a special case of object recognition. And when you are interpreting a face, you are synthesizing. You're not looking at every single individual element on that face. You're looking at an overall impression of the face. And as a result of that, one fact that we see is that faces show a powerful inversion effect. What that means is that if you were to turn the face upside down or invert it, you'll notice in this little graphic, the red line is when the person saw faces. And if the face is upright, they make very few errors in identifying the face. If the face is inverted or upside down, they make way more errors. And whereas houses upside down or right side up, it doesn't really affect the accuracy of recognizing the object. So faces in particular are very sensitive to whether they are upright faces or inverted faces. You're much more accurate at recognizing upright faces. Here's a classic picture from 1969, I think. 1980, sorry, 1980 on this one, because this is Margaret Thatcher back in 1980. She was Prime Minister of England at the time. And So old-timey Photoshop, we didn't have actual Photoshop. So they literally had to take a physical photograph and cut it apart in order to make these faces. And what they found is that people saw, let me invert it correctly for you. So people saw the one on the left as accurate. There was nothing wrong with it. People were saying, I don't see a problem. But when I turn it right side up, now it's on the right-hand side, you see the eyes and the mouth had been inverted. As long as the eyes and the mouth were inverted, people thought the face looked fine. They actually think the picture on the right here where it's inverted looks weird to them. And I think it's because you expect the mouth to be upright, you expect the eyes to be upright. And so when we flip it, and now we can see that the one on the right looks like a monster, you realize, oh, yeah, they must have just turned the mouth and the eyes, right? We're better at recognizing a face when it has the eyes and the mouth inverted, like in the case here on the left. People recognize that as Margaret Thatcher faster than they recognize the one on the right. So there's something about like parts of the faces, mouth and eyes in particular, but we think that with faces, you tend to see it holistically. Like you see that person. I was playing this little game on the internet one time where you're supposed to recognize whose nose is this, and it was supposed to be celebrity noses. And I have to tell you, I didn't get any of them. Like no, I couldn't recognize a nose separate from a celebrity's face to save my life. Even celebrities I'd seen a lot, I couldn't recognize their noses. And I think it's partly because we don't really look at the unique nose of someone, maybe, you know, in a really distinct, you know, love relationship where you're up face to face a lot, or maybe, but looking at these things in isolation is not how we process faces. We look at faces holistically, and that's why, you know, upside down eyes and mouth, that's part of our holistic recognition of Margaret Thatcher, you know, as opposed to when her face really was just completely inverted, people were not very good at it. So it's what we call holistic recognition, right? That's where we perceive the overall configuration rather than an assemblage of parts. So we don't look at the individual eyes separate from the face, or the individual nose, or the individual mouth separate from the face, or the teeth within the mouth separately. We tend to look at just the holistic picture. So the composite effect gives us further example of this. So in this picture, we have Hugh Jackman, who's going to serve as the top part of the examples that we're showing, and then Justin Timberlake is serving as the bottom. They did a number of different celebrity mashups like this. They found that when you're asked to identify who the celebrity is in the top half, people found it much harder to identify correctly the celebrity on the top when the faces were correctly aligned. When they were offset a little bit, like in panel B, people recognize Hugh Jackman much more readily. And I think it's because you, when confronted with a face, tend to look at it as a holistic thing. And it's hard to separate out, even though you can see a line where you can see the difference where they have a picture for the top half and a different picture for the bottom half. You can see that line. It still was a harder task for people to recognize that top half of the picture separately from the bottom half of the picture. Put it offset just a little bit like in panel B, and now people have an easier time of it. This is what we call the composite effect. If we put two faces together in a composite way, it can be difficult to sort of pull out the elements that make up one of the face versus the elements that make up a different face. All right, now I'm going to show you face perception over time from this study from 2019, Dobbs et al. So what they did was they had celebrity faces. Half of them were considered familiar celebrity faces because they were, the participants were American and the celebrities were American. And they'd already given the celebrity faces to like college students, and they rated them for familiarity. And then the unfamiliar faces were German celebrities that the American students found very unfamiliar in that ranking thing, so that's what they used. They had celebrity faces from America, celebrity faces from Germany. Okay, so those are our stimuli. And as you can see on this picture, you're shown the picture of the face for 200 milliseconds, and then the ISI is what's called an interstimulus interval, and that's going to be about 900 milliseconds. So that's almost a second. So 200 milliseconds is about a fifth of a second. The 900 milliseconds, almost a second, because a second is 1,000 milliseconds. So you see the stimulus for about a fifth of a second. You see the interstimulus interval, which is just a blank screen for about not quite a second, and then you see another stimulus. Sometimes it was kind of what you're seeing here, where you see the female face, and I'm not going to say who I think that is because I'm terrible at celebrity names, so I think I know who it is, but I'm not going to say. So you see that female face, then you see the interstimulus interval, and then now you see this male face. But sometimes you would see the same face twice. So you'd see that female interstimulus interval, same female. So sometimes you'd see them right in a row, same person. Sometimes you would see them out of order with a different person. Sometimes it was familiar faces, sometimes it was unfamiliar faces. It was all counterbalanced across all the participants. They used the reaction time of the actual brain, the moment of recognition is what they were looking for, using a magnetoencephalography process, where it's kind of like an MRI in the sense that it's doing magnetic stimulation. It's a much less expensive machine. So it's not quite as precise as an MRI, but it's really good at recognizing when brain activity starts, exactly, that it's good at time, right? So it can tell you exactly when the brain activity starts. And they were looking at a particular region of the brain that's really important for facial recognition. All right, and so here's the design. So half of the time it's a familiar face, half the time it's unfamiliar, and they're mixed and matched. And some of it's within subjects, so you might see a bunch of familiar faces. You're also going to see a bunch of unfamiliar faces, but then also between subjects, right? So we're comparing how you did on the familiar faces that you saw, but we're also comparing you to how other people did on familiar faces, and then the same for the unfamiliar. Half of the pictures were male, half of them were female. So again, that was something that was between and within subject. We were comparing you to yourself, also comparing you to the other participants. Some of the celebrities were older, some were younger. And then the last thing was like, who are they? Knowing their name. And that's called identity. So those are the variables that were being used. And here's one of the outcomes. They have a whole bunch of outcomes, but I thought this was a really interesting one for this analysis by synthesis principle. The gray bar that says image, what they were responding to is whether this was the same image for a second time. Are you recognizing that you just saw that person on the picture before? So that's the quickest response time. Shorter bars mean that you're responding more quickly. So that's the quickest response is, did I just see this one on the immediate picture right before this? The green bar is making the judgment whether this is an older or a young person. And so that takes a teeny tiny bit more time than just recognizing that you just saw this picture. The burgundy bar is recognizing whether it's male or a female in the picture. And that takes a little bit more time, but you'll notice these are very small differences, right? The recognizing that it's an image I saw before is like 48 milliseconds. Recognizing whether it's an older or young person, we're looking at like 60 milliseconds. That's a very small amount, remembering that 1,000 milliseconds is a second, right? So this is a very small fraction of a second that it takes. Recognizing the sex of a person takes about 75 milliseconds. And then recognizing who it is. When people, and this, not all of the celebrities were recognized, right? And so this is of those that they were able to recognize and offer an answer. It took a little bit less than 100 milliseconds to accomplish that task. So everything was happening really quickly. But you see the stair step of analysis. And what the researchers concluded is that coarse distinctions between faces in categorical dimensions are extracted before finer distinctions on an identity level. So if we just focus on characteristics of the individual, not that I saw this picture before, which is the gray bar, but instead we focus on characteristics of the individual. Are they old or are they young? Are they male or are they female? Those happen really quickly, and those are coarse distinctions, broad distinctions between people that we make very unconsciously and very quickly. This analysis by synthesis model says we do these kinds of analyses based on just sort of global characteristics, right? Like overall, very unconscious, very unintentional. It just happens really quickly that we can make those judgments about age and sex. All right, that's a good time to stop, but I'm going to forewarn you that what you're going to see next is a woman who has a condition called prosopagnosia. And this is a condition where specific damage to the brain has caused an inability to recognize faces. So check out this video, and when you're done, come on back. Well, it'll be in the playlist, so you don't have a choice. I'll see you afterwards.